Alright, so my talk today is about Newtonian noise. Oh, nice Kurt that you could make it. The kind of noise that will be novel in next generation instruments. And okay, so whoops, what's going on? I know what's going on. Right. Okay, so the trouble is shown here. So this blue curve represents the kind of sensitivity that we will soon have in our hands with the next generation telescopes like Advanced LIGO. And then here in red we have the curve that we call Newtonian noise. And here is like one possible target curve that is proposed for a third generation detector. And now the trouble really is that whenever nature says no, we say yes. And so somehow there must be something that we think that we can do about this. Alright, oh, there it works. That we can do about this Newtonian noise, because it's shown as in this graph here, it will completely dominate the instrumental noise and limit the sensitivity roughly below 10 or 20 hertz. Okay, so here we will see like a factor of 100 between other instrumental noise sources and the Newtonian noise curve. So let us first try to understand the complexity of the problem. First of all, what is Newtonian noise and how is it generated? So Newtonian noise are really gravity perturbations that are produced by any kind of density perturbation in the vicinity of the test mass. And now there are different ways to perturb density. So the most important one. Okay, let me try the other one. Yeah. So the most important one is the seismic field, and then we also have to take into account that there will be density perturbations in the atmosphere, and also any moving object in the vicinity of a test mass can cause a density perturbation. Now, I usually tend to focus on the seismically driven Newtonian noise, and because that's really least understood, and we don't really know how far and how well we can model and understand the gravity perturbations. So the best option that you have is not just try to understand the displacement field by deploying like huge arrays of seismometers. What you can instead try to do is to understand the seismic sources and then really optimize the design of the array that is supposed to give all the information that we need to model gravity perturbations. So, for example, what we have to consider is if seismic sources are transient or stationary, if they are distant or local, and if they are at the surface or deep underground. Then, given that the displacement field that is generated by these seismic sources is fairly well understood, not so much the sources, because seismologists never really looked at sources of seismic noise very much. They are to some extent understood, but not in the detail that we will need them to understand. So the field itself is well understood, and we know that it is that it comes in two different modes: the compressional modes and the shear modes, which are the transversal and longitudinal seismic waves. Then any surface can support evanescent waves that propagate along the surface, which we call fundamental Rayleigh waves. And in more complex geologies, we will have additional surface modes that can propagate on surfaces. And then these are the overtones and the Love waves. Then we have a special kind of field which we call near field, which we cannot decompose into compressional modes and shear modes as we do for the propagating far fields. And then we also understood very well how seismic fields reflect from surfaces and interfaces, and we also know very well how to describe scattering from heterogeneities. All right. So let's have first a closer look at the Newtonian noise that is generated by a seismic field. So these are like two Newtonian noise curves in strain, modeled using seismic spectra at the two LIGO sites, Livingston and Hanford. Now, we just saw that the third generation detector has some sensitivity target at 10 to the minus 24, above 1 Hertz, you could say. So you can see that we have to somehow decrease these estimates here by many orders of magnitude to come down to this 10 to the minus 24. Now, in general, there are two options. First of all, you can gain a lot by going to a quiet site. But then it will turn out that you still have to remove some of the Newtonian noise if you want to come down to 10 to the minus 24. And this is by doing Newtonian noise subtraction. And here I indicated how this may look like. If you pick like a quiet site, then just by that you will already gain quite a lot, so that the remaining subtraction that you have to somehow achieve is about 99% at 1 Hertz or 90% at 10 Hertz. So that's the subtraction goal. And now these subtraction goals actually also define these numbers that I give here. What do these numbers mean? So that means if you want to subtract 90% of the Newtonian noise, then you have to consider a volume which has a radius, like a sphere around your test mass, which has a radius of lambda half, where lambda is really the seismic wavelength. So at 10 Hertz, this could be like 200 meters for body waves, or it could be as small as 10 meters for example, surface waves, which are the relevant waves for advanced LIGO, for example. So fairly small if you want to do this. Here it gets already more complicated. 3 wavelengths at this frequency really means something like 12, 15 kilometers. So that's a larger volume that you have to take into account. But I don't necessarily want to say that you have to monitor the entire volume. You just have to understand the effects happening inside that volume. That's it. And well, so if you ever wanted if you can do something down at 0.1 Hertz, it seems to be quite impossible. First of all, you cannot really find a site which is substantially quieter than the LIGO sites at these frequencies, because this seismic noise is driven by the ocean waves, and this is essentially the same signal everywhere on the Earth. Now, so you would have to subtract 7 orders of magnitude of Newtonian noise, and I think that's quite impossible. Also, if you consider what the radius of the volume is 400 lambda, which means like 1 lambda is really 50 kilometers at this frequency, so it's the entire Earth, right? So that's quite unrealistic. Okay, so how does this work with the Newtonian noise subtraction? So concerning any other noise source, what we usually do is we try to isolate the test masses from any bad influence, and we try to idealize our system so that we somehow we always found a way to mitigate noise. But now the Newtonian noise is a little bit different, because there is really no way to isolate the motion of the test mass from the gravity perturbations. And so it seems that the only option that we have is then, in terms of isolation, to somehow use a seismic array and hope that the information we get from this seismic array tells us how to filter out the variance in our gravitational wave channel that is caused by the Newtonian noise. So we try to minimize essentially the variance using some filter that contains all the data from our seismic array, and this is a coherent subtraction of the noise, right? That's basically how it works. But now there are different options when you think about details, but in the end it's a little bit scary because in the end you generate like a very complex system. We already know from our controls that it actually makes us not understand the LIGO detectors anymore, because there's so much nonlinearities that we don't have like a really complete understanding of the LIGO detectors anymore, right? It's all much too complicated, and this will be another increase of complexity, and so it's like, that's why, right, we won't understand the experiment anymore, and also we leave much of the physics. So that means to understand and encode the meaning of our seismic data, we leave this up to machines, and they somehow learn to optimally make use of this And whether they are right or wrong, we don't know. We just know that they somehow fulfill the purpose, which means to minimize some variance. So I'm not really too scared about all this, but anyway, some people may. In general, what can we say about the arrays that we have to use? So we showed like early that if you have a homogeneous medium and your detector, that means your test mass, is far underground, then all you need to model the Newtonian noise is some detector, some seismometer, or some pair or whatever of seismometers at the location of the test mass, and this information will be all you need to model the entire gravity gradient or Newtonian noise. And this is because you understand this when you look at how actually the different contributions from different points interfere to generate the total Newtonian noise force. But this only really works in homogeneous medium. If you are near the surface, then it's already much different, and you would have to deploy some surface array with many more seismometers. So we are probably talking about 100 seismometers per test mass at the surface above the test mass. And now if you have like some heterogeneities in your medium, then you will have to monitor the displacement field close to these heterogeneities to really capture all the information that you need for your filters. Alright, so let's have a look at Newtonian noise from the atmosphere. This was already modeled a while ago by T.V. Creighton, and now let's discuss it in the context of third generation. That means we have two options. We can first say, okay, let's try to build our detector at the surface, or let's try to build it underground. So underground is probably more expensive. So that's why some people started thinking about a surface detector solution. Now what you would have, because of the Newtonian noise from the atmosphere, what you would have to construct are domes, huge domes around the test mass. And we're talking about hundreds of meter diameter. So huge domes, and probably not cheap either. But you can see, even if you do this, then you end up with Newtonian noise which is considerably stronger for this solution than for this solution. So we see a couple of curves here. So first of all, there are two ways atmosphere can generate density perturbation. First of all, you have like pressure waves that directly cause density perturbations, but then you can also have, like, if you want, density perturbations caused by temperature fluctuations that are somehow frozen in the atmosphere but are carried by some wind close to the test masses. So these are the two dominant mechanisms. And now for the pressure waves, you see that the dome is actually giving a very poor suppression. So this is what you get. This is Newtonian noise curve. For the underground, you have it much weaker, and you can understand this partially if you look at how a dome is suppressing the Newtonian noise actually just by a sinc function, whereas here for the Newtonian noise suppression underground you have an exponential function. Not really, I mean, the sky averaged, if you want, suppression is a little bit more complicated, but anyway, there is this exponential component in this, and that makes it much more effective to go underground.
So what's a good picture of shielding of the gravitational field? Is it the dome gets pulled away a little, and therefore...
No, you just prevent anything to happen within your dome. Oh. So you have no wind, and somehow you let the sound reflect from your dome wall, whatever.
Yeah, 100 meters.
Yes. All right. Okay. So I was asked twice, what about going inside the ocean? I really never considered this myself very much, but let's think about it because other people thought about it. So first of all, the Newtonian noise is actually pretty comparable to what we have in our ground-based detectors. surprisingly, I found that this is like almost identical values, just that it gets a little bit weaker at really low frequencies. But now you may wonder, why should we go into the ocean anyway? What is the reason to do this? I mean, maybe some people hope that we would have like less density perturbations. Okay, that's not the case, but I think the strongest reason is that water is so homogeneous that you can do like a much better subtraction of Newtonian noise. That was probably the motivation. Now, so that doesn't really make sense if you think about it. So first of all, we just learned that anything below 1 Hertz is like the density perturbations from anything below 1 Hertz will not just include density perturbations from the ocean, even if you are inside the ocean, but also essentially from the rest of the world. So it doesn't really matter where you are at these low frequencies. So that means that actually the idea is only good if you want to do like an incredible subtraction above 1 Hertz, say. So if like 4th and 5th generation we will have like 10 to the minus 26, maybe then that's the time when you want to look into this possibility. But otherwise I think it's pretty meaningless to do this. But anyway, so you also have like disturbances which are not like stationary from, for example, air gun arrays that for oil and gas exploration at the continental shelves, and then you have these major commercial shipping lanes and so on. So anyway, I don't really want to spend too much time on this because I don't really see a reason to think about it now. Another source is a working scientist. Now, you can make like simple calculations. So if you think about some 3 Hertz vibration of some scientist or whatever for some while, and just like 10 meters from the test mass, and just like 1 centimeter amplitude, and just 1 kilo of the body mass is moved by this, then you already get like a strain of 10 to the minus 22, which is like much stronger than the 10 to the minus 24 that we can actually see with these detectors. So what do we do about this? So this is 10 meters, so actually you can imagine that, so what is the distance and so on that we have to control in this way, and what are the options? So first of all, we have to take 2 things into account. So, so we not talk only about human beings, but we also talk about animals, right? And everything that's around there and can cause some kind of periodic perturbation of gravity. Now, it's actually, for example, not so easy to generate a chirp signal because you have to, because of the 1 over f squared, you have to get like really strong amplitude at high frequency. So I don't know what the likelihood is to generate some chirp signal inadvertently, just I don't know. But anyway, this is, I think, something, or we can use like this new Microsoft system. Anyway, you can monitor the motion of the scientists while they are near the test masses, and then feed this into your filters. That's, I think, not a big deal. You just have to know the density of these persons, but that's measurable, right? I think so the scientist is maybe not the problem, but if you consider something, still consider a solution at the surface, and maybe some upgrade of advanced LIGO may force us to think about this more closely, then what do we do with the animals and all this and the insects? I mean, to insects doing this on the vacuum chamber will cause like a perturbation that we probably see. So something to keep in mind. All right. Okay. So let's come to some measurements now. We have a project at Homestake, which is a former gold mine in the Black Hills, and there are various. So in fact, Homestake, the mine, consists of 500 miles of tunnels. It's it's for the US a very old mine. It's very deep. It's actually the deepest in North America, and now open to science. And we have on 4 different levels. We have seismometers, and the deepest level is 4,100 foot. And so we don't have too many seismometers, and so we don't have too many results, but we have some. So for example, we have measured the seismic spectrum at a depth of 4,100 foot. And there are 2 remarkable things. So first of all, if you compare this to the Hanford spectrum, so this is meter per second per root hertz. Now look at the 10 Hertz level at Hanford, there you have 10 to the minus 7. By the way, Hanford is noisier at these frequencies than Livingston. And at 10 Hertz, 10 to the minus 7, now if you look at our Homestake spectrum, then you are below 10 to the minus 9. So that's a factor of 100, and that's exactly what we need for third generation. So the question only is if we really have to go that deep underground to get this. Now, another thing I want to point out is that the spectral variation, so this is a spectral histogram, so you see like how much does the spectrum fluctuate around, and so how much time does it spend at specific values if you want. That's what these color show. And so you can see that the spectral variation is actually very small. Imagine this curve being plotted at 10 to the minus 7, it would be like a line that you couldn't hardly see. Whereas here at 10 to the minus 7 you have a huge variation. So it's like far from stationary, the seismic field at the surface, and not so much underground. But now back to the question, if we really have to go underground, we don't necessarily have to, because for example in Texas there's a surface station where you can see where the spectrum is really comparable to this one, maybe even weaker at some frequencies, with a little bit more variation, which is always typical for surface sites. But anyway, the point is just you don't really know how long this is going to stay like that, because there's actually there's one common reason for low noise above 1 Hertz, which I'm going to explain now. Alright, so we took data from some other experiment which is called the US array, and these are this is data from more than 1,000 different seismic stations, not all of them operating simultaneously, but anyway. So if you take the data from all of these stations, and what we did now, okay, I always forget it, I just have to tell you what this curve is here. This is like when you measure the seismic spectrum all around the world, and then you draw a line under all the seismic spectra that you measured, then that's this dashed line here, which is called the low noise model. Okay, so now this I need to explain for you to understand the colors here. So what we did, I did this with a student, was to take the seismic spectra and normalize it by the low noise model so that we can see how much above we are with respect to the curve, and plot this for all the seismic stations that we have. So the US array, by the way, is moving, or part of it is moving from the west to the east. That's why we don't have data there yet. But anyway, I will also explain why we don't need data there. All right. Where are we? Okay, so now you see everything is blue at low frequencies. That means we are pretty close to the low noise model, and this stays. Okay, so now we are getting close to these are about the frequencies of the so-called microseism, where the ocean is really determining the ground motion. And now interesting is what's going to happen above 1 Hertz, because there suddenly everything, not everything, but at places, and I think you can guess why, we suddenly see red colors showing up. And it's getting worse and worse the higher frequency you have. But still there are places where you still see blue colors. So what is the explanation for this? The explanation is it's always quiet when you are far away from human beings. It's, for example, very quiet in Alaska, and it's also pretty quiet at some of the points here in the Rockies or whatever. So, and these are all, well, not all I think, but most, well, 99% of all this is at least surface stations. So you find many locations with quiet surface stations. Now, important is, I guess we don't really want to have a third generation detector at the surface, but anyway, these are still favorable locations even for an underground detector, because it cannot actually get louder underground, right? So you have some guarantee that we don't mess up going there. All right, so what we then also did, I just want to point this out, is to somehow make sense of the data we saw looking at population density. Where are the water dams? The only information that we currently lack is the major rail traffic roads, which is very important, in fact. But anyway, that's work that will be done very soon. Okay, and now let me go and talk about scattering. So I think scattering is really the main reason why people in the past thought there is no solution to Newtonian noise, because everyone thought about, well, the ground is messy and dirty and it changes like materials changing from A to B, and we have scattering centers and it's a mess, and how do we want to monitor the field in a way that we can then predict gravity perturbations from that? That would have to be done with a very, very dense seismic array, and how bad is it really, was the questions we asked at some point. So now there are two ways to actually scatter a seismic field. And the first one, which luckily turns out to be not really a problem if you don't pick like a really stupid site, is the scattering from inhomogeneities inside the ground. So for example, this has been studied like by seismologists like plenty, but we also did something like this at the LIGO-Livingston site. So you may remember that there was this geoseismic survey from an oil and gas exploration company, and so what they did, they had like shot holes all around here, the LIGO detector, and they were looking for oil and gas. So they were okay, so the color here is actually not significant here, but it signifies the power of the blast as that was measured at LVA, for example. But anyway, you see that there are thousands of shot holes, and so we use the data to actually measure the scattering or anelasticity factor, the combined value, if you want, for the homestake, for the Livingston detector. So now there are various methods to do this, but what we did is to look at the spectra of the blasts. So first of all, what we did, we looked at the spectra of all of these blasts, and we stacked them according to their shot hole distance to the seismometer. Okay, so this is distance between the seismometer and the shot hole.
How did they do this in practice? Because the list of the blasts was factor and went back to the data and pulled the.
Yeah, so we actually got lucky because we got like the full log files from the oil company because the guy got laid off next day. So we had all the signs suddenly. Yeah, so we knew when roughly the blast was shot, and we also knew exactly the shot hole location. And so we knew the distance because we could identify all this from the log files. Anyway, so when you look at this at the spectrum of a blast, then you see that there are two maxima, if you want. There's one high frequency maximum, and there's one low frequency maximum, and these are actually surface waves, and these are body waves. So body waves would mean that the blast wave first propagates downwards and then gets refracted from a density profile and comes back again. So that's how you detect these body waves. Whereas these surface waves really probe only the first 10-20 meter of the ground and propagate as evanescent waves, surface waves, all the way. So you can see that these don't go far. So the method now works as follows. What you can see is, interestingly, that the centroid of this structure here is actually decreasing. So it goes down and down. And you can, if you now include in your calculations some damping factor, exponential damping, then this one actually explains exactly this decrease in frequency of the centroid. So you can then measure this, and from that obtain your loss factor for that ground. And we did that for the body waves and for the surface waves, and we found two Q values, and it then turned out, at that time we didn't know, but it really turns out to be typical. So the hard rock always has hundreds for the Q value, and the near surface layer, the weathered layer, the unconsolidated part always has like about 50. So that's quite typical, unless you are really considering sand or something, which is like a little bit messy. But anyway, and if you go into like hard rock, which is not sedimentary, but something like igneous or something like really strong, then you can get like Q values of 1,000 usually. So that's, and what this actually means is that the damping and scattering is so weak that we don't have to care about it, at least not for third generation. It's very weak, And if you are underground, then this relatively small Q value doesn't matter. So this actually means you cannot do 99% subtraction at the surface unless you find like the sweet spot on the world. But for underground detectors, it's quite reasonable to conclude that we don't have to consider this kind of scattering. There we go. Okay, but there's another type of scattering, which is scattering from surface topography, and that is something that really is a little bit more tricky. So there's a simple case where you have a plane surface, and then, for example, you consider an incident plane compressional wave, and what happens in this very simple case is that it gets reflected, and there's one reflected pressure wave or compressional wave, and then you have also conversion into shear waves. This always happens because you have to fulfill boundary conditions here. Now, and you always have the fundamental Rayleigh mode, which can travel independently from these here along the surface. Now, if you consider like a realistic surface, then actually this simple picture doesn't hold anymore, and you get a scattering matrix which couples all of these modes. All right, so this is complicated, and I thought like, how do we calculate this? I was hoping that someone else did it already, and in fact, yes, someone did. So to understand this, let's start with a simple example, that because optics is always simple compared to seismology. So imagine a surface. This could be a mirror surface, but it can also be an imaginary surface. And now consider an electric field or light, whatever field, propagating through that surface. And now you look at the field on this plane. All right. So and then you take the spatial spectrum of this field. So you look like what wave numbers describe my lateral shape. And now what we know from optics is that actually this spectral shape spectrum here is determining the field away from this plane here, and it's actually happening the following way. The large scales in this spatial pattern, these scatter normal, or so the contributions will propagate normally to the surface, which is real or imaginary, whatever, or virtual, and the smaller scales will actually cause what we may in some way say the scattered field, cause like scattered fields to propagate like at some large angle to this normal direction. But then you can also continue and say that the smallest scales, the scales that are smaller than the wave number of the light field itself, which is omega over c, these will trap the field energy into evanescent waves propagating exactly on that plane. So any small scales, anything smaller than this omega over c, or higher wave, if you want higher wave numbers than omega over c, will be trapped and propagate normally. So that's what we know from optics. And okay. And this also happens for seismic waves. And let's just look at this picture. So an incident seismic wave will, on some plane, the surface here, have some horizontal wave number if you want. And also the surface topography will now be described by some specific scale, described by this wave number kt. And now this wave will be scattered into 3 different components, or reflected, so you have the specular reflection, but also like a plus minus kt component. And now you can see that if this kt is large enough, then it will scatter actually into a evanescent field. And also you actually have 2 sets of these, because you also partially convert into shear waves. So that's the complete complexity of the problem. But anyway, so this is not like just theory. I think we already saw this in our homestake data, because we have like excavation blasts deep underground, and these get reflected as body waves from the surface. And what we actually see is a Rayleigh wave following the body wave signal. And so this is then certainly some conversion from body waves into surface fields. So we don't have the array yet to completely analyze that, but I think we can at least make this qualitative statement. Anyway, in reality, what you would have to do is like look at surface topography, for example, here at Homestake or here at Livingston. Livingston is very flat, and the amplitudes of that image, like the wave numbers, will actually determine the scattering coefficients, and so that's how we can then predict that at some place scattering will be so bad that we are like lost, or it will be weak enough and we can even neglect these effects. If we cannot fully neglect it, but mostly, then we can still hope to get the information with some surface array. Alright, so I'm getting closer to the end. I hope there's still enough time left. Good. So I decided to put some to-dos on my slides. So there's actually still theory. Until yesterday I thought that we are almost at the end with theory, but then yesterday it changed a little. But anyway, I will tell you about this on my last slide. But so before yesterday I thought this is the only theory problem that still remains. And if someone knows, so I'm actually asking a question, if someone knows how to calculate this integral, then let me know, because I really don't know. So it seems to be very simple. So you have, the point is the near field. So you want to calculate the complete, so the integrated gravity perturbation from some displacement field that is generated by a point force at some distance to your test mass. And you can see that this that the near field, at least, of this point force that is generated, that the near field looks like a dipole field. So that's the shape of the dipole. But it's centered at around some point where the force actually is acting. And then also the way actually the displacement field generates gravity perturbations, again a dipole form. So that's why you have another dipole shape here. And so the total integral is actually not a dipole-dipole interaction equivalent, because then you would just insert a dipole moment into this formula, but actually you multiply complete dipole fields, which is pretty unusual. That's why I don't find any solution to this in the literature. But anyway, maybe some post-Newtonian guys have seen integrals like this already. In the end, we always have the numerical solution, and here we have the dipole field, and it behaves like all fields in the end, like a plane wave field qualitatively. So you can see here contributions, let's say how Newtonian noise builds up as a function of integration distance from your test mass. And you can see that most of the Newtonian noise is already like formed after lambda half, and this is actually a characteristic number. Lambda half is like the distance out to which, we saw this before, you have 90% good accurate prediction already of your Newtonian noise, and here you gain only a little bit if you integrate further out. But anyway, so from this we can actually deduce that this will not be like terrible, but still we may want to have the integrated value just to say, for example, a microfracturing event close to our test mass, which always occurs in rock, is generating this and this gravity perturbation, and so we should be able to make some prediction of that. The to-do in terms of data analysis, there's really not much left, but what we should understand is really how to set up the optimal array that analyzes the seismic field. And this is mostly a problem of the surface array that we will need. And so what you always want to do is you want to be able to estimate the spatial spectrum of the displacement field. So you look like what is the amplitude at some wave numbers. And so this, for example, is the estimated spectrum that we got from the geophone array during the blast survey at geoseismic survey at Livingston, but now for some seismic noise between blasts. And so you can see that at each moment in time you have like a few components actually contributing to this seismic field. But this picture looks very bad because we had like not a really good array. But anyway, so the question is, how do you get the optimal estimate of this? If you do like what seismologists usually do, but not all of the time, but what they usually do is they just do some simple cross-correlation of data streams, and then from this they somehow derive spectra. Like it's very similar to time series analysis actually. And the optimal way to do this to do this specific method is to apply window functions, for example, which actually suppresses data from the edge or surface of the array, which is like kind of stupid. I mean, we do this all the time with time series, like throwing away data. But setting up an array and then actually suppressing data from the ones that cause most work, that doesn't make sense to me. So, I mean, can we do something else? And I think we can. So maximum likelihood estimates of the spatial spectrum have been considered already by seismologists, but I think they don't really fully appreciate the advantage that comes with these. So first of all, maximum likelihood estimates don't require us to throw away data, and therefore we can expect better estimates. And in fact, some seismologists have analyzed this to some extent and found really that spectral estimates got much better. But then the question is, if we say, okay, let's do it with some maximum likelihood method, what is the optimal array design? So we know this is somehow the optimal shape for this traditional method, but what is the optimal shape for a maximum likelihood method? So that's, I think, the problem we still have to look at. And in terms of experiment, there's a list. I think we should really make use of the fact that advanced LIGO will be able to detect Newtonian noise. I don't necessarily say that we will be able to, or that Newtonian noise will limit advanced LIGO sensitivity, at least not in the first version if you want, but it will definitely be able to detect the Newtonian noise because it's like marginally touching the sensitivity curve, the Newtonian noise. And so for that reason we should really start some small experiments in the beginning, like studying correlations of the seismic field, and also monitor, for example, vibrations of the building, then also try to characterize the atmospheric spectrum. So for example, it really matters a lot if sound in the atmosphere propagates like mostly horizontally or it comes vertically, because horizontally is much better because the wave number on the surface is very small, and so any suppression effects as a function of depth will be much stronger. So it's always, for underground detectors, good news if sound actually propagates horizontally. Yes, and then eventually, hopefully, detect Newtonian noise, be it from seismic noise or at least from earthquakes. And then at Homestake, we have to continue the analysis of scattering and also use it as a test bed for low noise seismometers, and then in the end really do like a three-dimensional array, something that people haven't done really much in the past, because you really want many, like maybe 100 or 50 seismometers, and then deploy like a wide array like with STS2 or something. So that's actually getting quite expensive, but that would be needed to characterize the seismic field and understand what's going on really with scattering and everything. Okay, so now my last slide, and I just like calculated this yesterday, and I didn't fully appreciate what we will be able to do with third generation detectors. So imagine that our Newtonian noise signal shows up like this, but our seismometers don't show anything. What does it mean? So what this means is that somewhere a seismic wave is propagating that never reaches the surface. So what can this be? So you may know, so we have the crust here, and then like, well, the thickness of the crust is varying, but like most of the time it's about 50 kilometers or something, or a little less. But so then you have an interface between the outer mantle and the crust. And Rayleigh waves can propagate everywhere. They can propagate at interfaces. I think then they are not really called Rayleigh waves anymore. But the point is there can be evanescent modes propagating along these interfaces that we will never see at the surface. So now actually I took like, I simulated now an interface at 100 kilometer depth, and I took this displacement of the interface, and so I get this strain signal, which is like 10 to the minus 22 in its peak. It's huge. It's like a factor 100 stronger than what we can actually see. And I mean even greater. So this is already great for seismology. But now I figured out that yes, I mean we can do much cooler things. So for example, we can even see waves propagating at the mantle core boundary, and maybe even cooler, we can see modes of the core, like the solid inner core. And so the problem with that one here is that actually the reflection coefficient between the liquid outer core and the solid inner core is very small. There's a small impedance contrast, as you say. But so maybe the Q, if you want, of that cavity of the core, if you look at the core as a cavity for seismic waves, it will not be very strong. But maybe we can see it. But anyway, the impedance contrast between mantle and core is huge again. So you will definitely see it. And also, if you think about it, any earthquake around the Earth, we will be the first to see it, right? Because it propagates with the speed of light to us, and so that's fantastic. Because if there's an earthquake here and it produces, it's huge, like magnitude 8 or something, then it will take like 10 minutes before it comes to us. But maybe we see already like 5 minutes before, we will see oscillations going on here, telling us something about the structure of the Earth before we fall out of luck. I mean, that's pretty awesome, I think. And people currently do all kind of imaging techniques and tomography, but they can never really sure about their models. And we have like a direct access to all this using some strong earthquakes. And I think that's neat, because that's more science in our gravitational wave detectors than we thought, I think. All right, but that's actually everything I want to say. Thanks for your attention.
To see some of these effects.
Virgo? Yeah, I don't know. I've never looked at this, but I would be. The problem is, at the moment, all Virgo can do is like, so the seismic disturbance has to be pretty close to the test mass. Now, we thought about this actually at Tama. So what happens? The seismic wave comes, but in fact you can calculate that the current detectors see the gravity gradient or the Newtonian noise too late. So there's only like 1 millisecond between losing log and seeing Newtonian noise. Okay, so because then the seismic wave is already there. Whereas for third generation, we are so sensitive that we can have plenty of time for this.
Totally into trouble if we make the ground like Swiss cheese by putting seismic stations all over the place and thus creating.
Yeah. I mean, yeah, maybe. So I can't give like a ultimate answer to this, but for example, the volume of the Homestake mine seems to be completely perforated, like 500 miles of tunnels. You see like level over level and tunnels everywhere, but in fact if you calculate the total volume of this, it's like tiny compared to the complete rock volume. And you can calculate a scattering coefficients from this, and you find that the scattering even from the mine structure itself is like quite small, although it may already start to be significant for Homestake. Scattering always matters locally when you measure at the tunnel, so you want to, but like if you want to have the complete cross-section of the scattering by the mine volume, it's small. So I don't think that there will be an overall significant disturbance. We only have to understand, if you want, locally reflection from tunnels, because that really matters for the very data that we measure with a seismometer. But otherwise, I don't think that this is like too bad in terms of gravity gradient or Newtonian noise.
Educating at Homestake, because it's the only place. What fraction of the overall knowledge that you gain is going to be to that site?
Yeah, I think so. I think that I don't know yet, but as far as I can tell from the measurements I know, the underground fields always look very similar. This is because we have a high Q value and most of the seismic disturbance comes from far away. Now, the sites may always differ in what is generated at the surface locally, so that may be very different, and so there may also be some significant differences in the underground seismicity. But I think as long as, Homestake actually is already like a bad location if you think about it, because it's like so messed. I mean, the geology is very complicated. So maybe, yeah, difficult to answer. I mean, in the end, what you really want to understand is how to estimate, for example, a wave number spectrum of a seismic field. What is the density you require? You characterize scattering at homestake, so then you may actually give boundaries for scattering at other places that are less complex, for example, and so on. So I think it's all very useful what we do, but I don't think that it will be 100% analogous. So, but yeah, I think there's nothing truly homestake specific, because we can always somehow relate this to other sites, I think.
I've got one actually.
Yes.
Or two. One. Why is Nebraska so red?
Oh, yeah, good. Oh, I didn't say this. Yeah.
Question. Why was Nebraska so red at 1/3?
Yeah. So this is actually, yeah, that's a good question. So actually, what happens is there's like coal mining in Wyoming, and then there's like a major traffic, like train traffic through Nebraska, and that is disturbing everything there. So that's why I think it's really important to get the traffic density data from trains, but I have to like be club member. I don't want that. So I don't have the data yet, but yeah, I think it's important to look at it, because it causes much of the seismicity at higher frequencies throughout the US. Yes. Yes. That's right. That's right.
Take a metal sphere, so then they would very loosely much bigger than the ground, because that's what the scattering experiment is. Know what's the cross section of that?
Wait. Do you say that the wave, that the sphere is much smaller than the seismic wave?
Yeah.
Okay, so this is, the Rayleigh scattering is always like, so there's this V over lambda cubed factor, but then it really also, you have to take in, well, I think that's mostly it, except for if you, for example, study distributions of this, then you have a correlation length of these spheres in your medium, and then you will get like another correlation over lambdas or something in that formula. But it's like, in the end, it's a 1 over lambda to the power 4, I think, the cross section. So that's why it's so small, the effect.
We have refreshments in the